Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll have a review of congruence. So before we get to congruence, we need to have a quick go over angles and parallel lines because they come up with congruence. So remember, two lines are parallel if they never meet, and we usually denote that they're parallel by putting arrows on the lines. So there are three types of angles that we learned with angles and parallel lines. So the first makes this C shape here. We say that these two angles here are co-interior. Also, these two angles here are co-interior, so it can be a back to front C. So co-interior are the angles that aren't equal. When we're talking angles in parallel lines, they are supplementary, meaning they add to 180 degrees. So what that means is that this angle here and this angle here, both of them add up to 180. If this one here was, say, 100 degrees, then the other one down here would be, say, 80 degrees. So the next type of angles that we're looking at form this Z shape here. So this angle and this angle, as well this angle and this angle, they are what we call alternate angles. So alternate angles are always equal. So like if this angle here were 70 degrees, this angle here would be 70 degrees. That would mean that this angle here would be 110 degrees and this angle here would be 110 degrees as well. All right, the last type of angles that we're looking at form an F shape. They're corresponding angles. So this angle and this angle are corresponding. Also this angle and this angle. So it can be an F, it can be a back to front F, upside down F, or whatever. So just like alternate angles, corresponding angles are equal. So if I told you that this angle here was 120 degrees, then so too this angle would be 120 degrees. So it turns out this black angle here would also be 120 degrees because these two angles are vertically opposite. So I didn't include them when I said there are three types of angles for angles and parallel lines. The reason I didn't is because vertically opposite angles are equal regardless of whether the lines are parallel. Whereas co-interior angles are only supplementary, alternate angles are only equal, corresponding angles are only equal if the lines are parallel, if there are parallel lines. So these rules only work if the lines are parallel, whereas vertically opposite angles work regardless of whether the lines are parallel. The reason vertically opposite angles are equal is because that 120 degree angle and this angle here, they're supplementary, add to 180, but the yellow angle and this angle are also supplementary. So the only way this could work is if these two green angles are equal. By a similar argument, these two angles are equal. Vertically opposite means they're facing each other when they're standing up. So we're going to use this to find the value of some unknown angles. So here we have a diagram with some parallel lines. We're going to find the value of each of the pronumerals, and we need to give a reason each time. So let's start with W. So W is vertically opposite to that 60 degree angle, and vertically opposite angles are equal. So we just write W equals 60 degrees, reason in brackets, vertop, of course, short for vertically opposite. So X is also 60 degrees because it is alternate to that blue angle there. They make a Z shape. So Z is the one I'll do next, is co-interior. So remember, co-interior angles are not equal, they add to 180. So for Z, you're like, what number do I have to add to 60 to get to 180? And that's 120. So Z's 120 degrees because it's co-interior. Y is actually corresponding to that 60 degree angle. It makes the F shape. So it's equal, corresponding angles are equal. So we need this because sometimes we'll need to use these rules in order to prove that triangles are congruent. And I'll show you an example of that later. But first, we're just going to go through what congruence actually is. So let's look at the green shape on your screen, a parallelogram. We're going to apply to it each of the three basic transformations: translation, rotation, and reflection. So let's start with the translation. So that's just a slide, so we just take the shape and move it to another location. So when we do that, we usually label the new vertices with a dash. So A goes to A dash, B to B dash, and C to C dash, and so on. So next up, what I've done is flip the shape, or reflect it. Once again, I put dashes on the vertices of the new shape, the image, to indicate that this is the shape after it's undergone the transformation, in this case, a reflection. So the final thing I'm going to do to the original shape is rotate or turn it. So sometimes it can be hard to see which transformation has been applied, whether it's translation, reflection, or rotation. To do that, the vertices will give you a clue. So note for the translation, the vertices were translated. They stayed in the same orientation. Whereas when it was reflected, the vertices were also reflected. So C and D moved to the top, A and B to the bottom. And for the rotation, you guessed it, the vertices were rotated. So C kind of took the place of A, and then A took the place of B, and so on. So the reason I'm showing you all of these, all four of the shapes on your screen are congruent. This means that all four shapes have the same side lengths, the same angles, the same area, the same everything. They are, for all intents and purposes, the exact same shape. So if you take any shape, it wouldn't matter whether or not the original shape was a parallelogram, but if you take any shape and rotate, reflect, or translate it, you get another shape that is the same size, same area, same side length, same angles. You get a shape that is congruent. So two shapes are congruent if one is just a rotation, reflection, or translation of the other. So if we wanted to tell whether two shapes were congruent, normally we would need to check that they have the same set of sides, the same set of angles, but triangles represent a special case. So we're now going to look at congruent triangles. So when it comes to triangles, we don't need to check if every pair of sides, every pair of angles is equal in order to determine whether or not they're congruent. We only need to use one of the four tests. So if any of these tests is satisfied, the two triangles are congruent. So the first test, SSS, so remember S means side, it means if all three sides of the triangles are equal, there's three pairs of equal sides, we don't need to check the angles because we know that they will be equal as well. So SSS, three pairs of equal sides, is sufficient to determine congruence. So when triangles are congruent, we need to write a congruent statement. So what we do is we write triangle. I can call the first whatever I want, A, B, C, and we use this symbol here to mean that they're congruent. Now for the second triangle, what I need to do is I need to line up the vertices. So because A was written first in the first triangle, in the second triangle is the one that corresponds to A, and that is D. This second triangle, the one on the right, is just a translation of the one on the left. So I can find the vertices pretty easy. So A corresponds to D, B corresponds to E, and C corresponds to F. And I usually write the reason, the test I used, in brackets. So that's the congruent statement for the first one. So let's look at the second test, SAS. So that means two sides, because there are two S's, and an angle, but it must be the angle between the two sides. So many people mess this up. If I have, for example, these two triangles, these ones in black, I can't actually use the SAS test because I have two equal sides, one pair there, another pair here. That's what the dashes mean, equal. But the angle, I'm told, is not the angle between those two sides. I would need to have this angle here in order to prove congruence. So if I don't have that, which I don't have in these two triangles, I can't use the SAS test. But if we look at the triangles in green, I can use the SAS test because I've got one pair of equal sides and then a second pair of equal sides. That's what the dashes mean. But the angle that is equal, which is marked with this arc, they are the angles in between the two sides that I'm given. So then I can use the Sas test. So remember, Sas test, it must be the angle between the two sides. So the triangle on the right is actually just a reflection of the triangle on the left. So the vertices will have also been reflected. So if I want to write the congruent statement, I can call the first whatever I want. So I'm just going to call it GHI is congruent to triangle. Now I need to line up the vertices. So the easiest way is to look at marked angles if you're given them. So I've got that this angle and this angle are equal here. So this angle occurs at G in the first one and K in the second one. So that means G corresponds to K. So I, the vertex I, it's where the line with 2 dashes meets the line with no dashes. So that is over here. It corresponds to L, where the 2 dashes meets no dashes. So that means L goes last and H corresponds to J. So I go KJL, and the reason was SAS. Okay, for the next test, it's AAS. So that means it's 2 angles and a side. AAS is easier because it doesn't matter which 2 angles or which side. Just if you have 2 pairs of equal angles and 1 pair of equal sides, those triangles will be congruent. You don't need to check the third pair of angles or the other pairs of sides. So the second triangle, the triangle on the right, is a rotation of the one on the left. So the vertices have also been rotated. So to write the congruent statement, I call the first whatever I want. So I'm just going to call it MNO, and that's congruent to, that's what the 3 lines mean. So we can find which vertices line up with which by looking at the angles. So the one with the dot here and here, N and P correspond to each other. The one with the arc means O and R correspond to each other. And the one that is not marked means M corresponds to Q. So M corresponds to Q, N corresponds to P, and O corresponds to R. And the reason in brackets again is AAS. Okay, the last test, RHS, is one you can only use if the triangles are right angled. So R means right angle, H means hypotenuse, which you probably know is the longest side of a right angled triangle. But I want you to be careful. If you're given 2 right angled triangles, it doesn't necessarily mean you have to use RHS. You might use SAS, AAS. So the RHS allows us to overcome this rule up here. Normally, when you have 2 pairs of sides and 1 pair of angles, it has to be the angle in between. But because of Pythagoras, it means that in this particular case, we can get away with this angle not being between the 2 sides, because Pythagoras actually means that the third sides will also be equal. So here we have 2 pairs of sides and a right angle. Note SU, this one here is the hypotenuse, VX is the hypotenuse. So the second triangle, the one on the right, is just a translation of the one on the left. So if I wanted to write congruent statement, I just write triangle, call the first one whatever I want. That's congruent to. So the one corresponding to S is V. T corresponds to W and U corresponds to X, and the reason is RHS. All right, the final thing I need to go through is proving that 2 triangles are congruent. We're going to write a formal proof. So in each of these diagrams, there are 2 triangles that are congruent to each other, and we are going to prove that they are congruent. So we're not just going to write which test proves they're congruent. We're going to say why sides are equal, why angles are equal, and so on. So let's look at the first one, which is this one over here. So in this one, we have like one big triangle divided into 2. So first we've got to work out which test we're going to use. So in this first one, we are given 1 pair of equal sides and 1 pair of equal angles, that's 90 degrees. We also have that there is one of the sides, AC, is in both triangles, so it must be equal in both triangles. So even though both of these triangles are right angled, This is not RHS because we're not told that the hypotenuse, which is this side over here of the first one, is equal to the hypotenuse over here. We don't know X is 4 until we prove that the triangles are congruent. So because we're not given anything about the hypotenuse, we're not told they're equal, we have to use SAS rather than RHS. So let's go and write what I just said. BC equals CD. We were just told that, didn't have to use any mathematical deduction for that. So we just put in brackets given, and same with the two angles being 90 degrees. Now the way we write the third one is AC is common. It is in both triangles, so it must be equal in both triangles. So I've shown that I have two sides and the angle between them. That's enough to show that these two triangles are congruent, and thus I write my congruent statement. So this here constitutes a formal proof. I've said why things are equal and then written my congruent statement. So then that becomes clear that X must be 4 centimeters because they are corresponding sides of a congruent triangle. So let's now look at the second one over here. So I'm not given too much information. I'm only given that one pair of sides is equal. So now I'm going to have to look at some equal angles. Well, thank God we had a quick tutorial on angles and parallel lines, because I know that these two angles are going to be equal because they're vertically opposite, and these two angles are going to be equal because they're alternate. So I can use the Aas test. So I first write that GH equals GF. Those two sides were equal, and that's given to us. Now these two angles in the middle being equal, it wasn't given to us. So we have to say the reason that they're equal, and that is that they're vertically opposite. And finally, the two angles that are alternate. I have to say why they're equal. So angle GHI is this one here, and then this one here is GFE, and the reason is they are alternate. So that's enough to prove congruence because I've got two angles and a side. I now write my congruent statement. So I've now shown that these two triangles are congruent, so that means that Y will be equal to 10 millimeters because it corresponds to EF. Now Z is equal to 80 degrees. I didn't actually need the congruent triangles to show Z was 80 because it's alternate anyway. But now that I know that the two triangles are congruent, of course, Z must equal whatever this angle is here because they're corresponding angles of a congruent triangle. All right, sorry for the long video. Thank you so much for tuning in. This has been the luckiest maths teacher in the world. Have a great day.